let's take a look at this structure that we had looked at in our statics review. Now, we've already found the loads, and we did our static analysis, so we know that in AB, we have 40 kilonewtons of internal compressive force, and in BC, we have 50 kilonewtons of tensile force. So, can this structure safely support that 30 kilonewton load? Well, once again, we can't tell from just the just the forces. The forces are not what's important. What's important are what the stresses. We have to calculate that force density. But before we can and what we have to do then is we have to compare it to what the allowable stress would be of the materials. So right off the bat, we don't have enough information listed here to actually solve the problem. So let's go and let's write in that information that we need. Just trying to, okay, we've got the right color. And so the first thing is we have to look at the material. So let's say that our material is, we're going to use some kind of steel, so SKS steel. And we will say that that has an allowable stress of 165 megapascals. What does allowable mean? That means that if we go above that 165 megapascals, the system will fail. Now we have our two members, so we have this 20 millimeter diameter rod, and then we have this bar that's 50 millimeters wide, and let's say that it is 30 millimeters depth-wise into the board. So it's got a cross-sectional area of 50 millimeters by 30 millimeters. So now what we're going to do is we're going to calculate out the stresses and compare them to the steel. Now actually, if you look up steel, it's going to tell you 165 megapascals will be, typically the material will not list out both a tensile and a compressive failure stress. And that's because mostly it's 165 would be its failure in either compression or tension. Some materials, glass, concrete, will have separate compressive and tensile stress ratings, but right now the material that we're using is just going to be one. So it's either 165 megapascals compressive or 165 megapascals tensile. So what do? Well, we apply our stress definition. Normal stress is the force over the area. Now, sometimes I use F. I should be consistent and use P, which is the typical designation for normal force. So let's look at member AB first. So remember, AB is our bar, and its load was negative 40 kilonewtons of compressive force over its area. So it's the cross-sectional area. So how do we find the cross-sectional area? Well, if AB is the bar, that is 30 millimeters by 50 millimeters. And there we go. Now the problem is if you look at the units here, these aren't going to work out because these are going to be kilonewtons per millimeter squared. We need to have meters squared. So what we're going to have to do is we're going to have to multiply this by 1 meter is 1,000 millimeters. Now, I see this happen all the time is the students will stop right there. Because, oh, 1 meter is 1,000 millimeters, that's a conversion. That's not true because we're looking at square millimeters to square meters. So what you have to do is you have to take this conversion factor and square it. And so now you're going to have square meters. If you just did 1 over 1,000 millimeters, you're going to be off by a factor of 1,000-ish. Actually, maybe more, but because you'll have only converted one of the 2 millimeters to meters. This way you get them both. We calculate that out, and so it's negative 26.67 times 10 to the 6th. This is engineering shorthand. E6 just means times 10 to the 6th pascals. And that is negative 26.67 megapascals compressive force, compressive stress. And that is going to be less than our 165 megapascal of stress. So AB is fine. So AB will not fail. Now the system can still fail if it fails at BC. So now let's do the same thing for BC. Stress is load over cross-sectional area. The internal load in BC was 50,000 newtons or 50 kilonewtons. You're going to divide that by its area. And so the area it's a 20 millimeter diameter area. So that's pi over 4 times 20 millimeters squared. Got to do the same thing. It needs to be in meters squared. It's not millimeters squared, so 1 meter is 1,000 millimeters. And once again, we have to do that twice, so we'll square that. And if I go and solve that, that's going to be 159.15 times 10 to the 6 pascals, tensile stress, or 159.15 megapascals. And so that tells us that it definitely will hold that weight. It will not fail. One thing to note, this 50,000 kilonewtons is only 20% higher than that 40,000 kilonewtons in the rectangular portion, but the stress is 6 times as high. Once again, it's not about the load, it's all about that force density. And so that's why it's very important for what's going on. Now let's take a look at this at the design side. So we're going to flip this a little bit. So say that this was a structure on the ship, and it was holding a piece of equipment, cantilevered over something, whether it's a compressor or whatnot. And the steel bar breaks. So this breaks. It's useless. And so we have to replace the bar, but we have no steel bars left on the ship. But we do have a bunch of aluminum bars. So the question is, what diameter of aluminum bar would you need? Now, this comes into a problem because the allowable stress for aluminum is only going to be 100 megapascals. So it's a material that's not as strong as steel. So if I look at this and go, okay, well, my stress is going to be my load over my area. Now, at this point, I know the load is going to be 50 kilonewtons. I don't know the area, so I'm going to go to solve the area. But I know my allowable stress is 100 MPa. And so I'm going to rearrange this equation so I can solve it. And so the area is going to be equal to 50 kilonewtons divided by 100 MPa. And let's actually write this out. So 50 e to the 3 newton meter squared. This is 100 e to the 6th. Sorry, this is just newtons, not newton meter squared. And this is e to the 6 newton per meter squared. Those newtons will cancel out. We're going to be left with meters squared, which is what I expect from my area. And so that's going to be 500 times 10 to the negative 6 meters squared. Now, I'm looking for the diameter of the rod. So A is going to be pi over 4 d squared. So that means my diameter is going to be 4 times area over pi. Take the square root, just rewriting the equation. So 500 e to the negative 6 meters squared is my area times 4 divided by pi. It's 3.14. Raise that all to the 1/2 power, and that's going to give me a diameter of 25.2 millimeters. So now if I need to use an aluminum rod, what I would be looking at is I would need something with a diameter of 26 millimeters, because you're not going to get a rod that's 0.2 millimeters. So it's basically around 1/4 of an inch rod to make that repair. And so that's how we can use and calculate normal stress using our equation. And once again, it's all about that internal force. That is the most important thing. If you have any questions, please let me know, and I'll see you in the next video.